Hello everyone, my name is Ruben Martins and I will be presenting our work today on a formal verification of a mixed-stress synchronization protocol. This is joint work with McCall, Dionisio, Amit, Bjorn and Mark at the Software Engineering Institute, John at Carnegie Mellon University and Hyoseung at UC Riverside. This material is based upon work funded and supported by the Department of Defense with Carnegie Mellon University for the operation of the Software Engineering Institute. Cyber-physical systems are used in many safety-critical applications. However, verifying these complex systems is a challenging problem, since current verification techniques do not scale to this complexity. So how can we trust the system and verify every component and their interaction? We propose not to verify every component, but instead to take advantage of the recently proposed mixed trust framework. In this framework, untrusted components interact with trusted verified components. The trusted components are responsible to ensure the safety of the system and provide both timing and functional guarantees. Let's look into the mixed trust framework in more detail. In this framework, we have two kinds of components, untrusted and trusted. The untrusted components will perform some computation and output an action A as the result of its computation. The trusted component is responsible to check if this action is safe and that the action is performed on time. If the action is safe, then the system will perform the same action. Otherwise, a default action is performed instead. For the purpose of this talk, we will denote these trusted components as enforcers, as they provide formal guarantees since they are protected by a verified micro-hypervisor. Mixed trust frameworks are great since they allow us to combine untrusted and trusted components in a symbiotic way. However, even if the trusted components are verified, the system can still be compromised if the interaction between untrusted and trusted components is not verified itself. In this talk, we will focus on timing guarantees enforced by the trusted components, and we will assume that the action performed by the untrusted component is always safe. An untrusted component is composed of periodic tasks that execute a job and then wait for the next period to execute a new job. We will denote the periodic task in the untrusted component by guest task. This task is guarded by an enforcer in the trusted component. We denote the task that runs in the trusted component as hypertask, since it runs in a verified micro-hypervisor. The hypertasks ensure that there is always an output at the end of each period. From a timing perspective, this output can either be the one from the untrusted task if that task finishes on time, or a default output from the trusted task that is used in cases where the guest task did not finish on time. Since we're talking about the timing behavior of the guest and hypertasks, we will need to consider the schedulability of each task. Let Ci here be the worst case execution time for the guest task. We can compute a EI such that it's always feasible for the guest task to finish its job in normal circumstances. In similar fashion, let's consider KCI the worst case execution time for the hypertask. We can also compute these values such that di, the deadline for the hypertask, is large enough that the hypertask will be able to perform its computation and finish on time. So as you can see here, then the period is then divided by these components, where we have some time that is dedicated for the guest task, where the guest task can run its job, and then some time here where the hypertask can then enforce its behavior. For simplicity, we will consider in the remainder of this talk that the deadline for the hypertask coincides with the end of the period. It is important to compute EI such that both guests and hypertasks will have enough time to finish before their respective deadlines. Details of this computation can be found in prior work of Dionisio that was published at the International Conference on Embedded and Real-Time Computing Systems and Applications. To ensure the correct behavior of the mixed trust framework, the following conditions must hold throughout the execution of the system. Condition C1, each mixed trust task must produce an output every period. Condition C2, there is only one output per period. Condition C3, the output produced by a task in a period is either from the guest task or the hypertask. C4, a guest output must be the product of a computation that executes within a single period. And finally, C5, the hypertask must execute E times units after the arrival of the job it guards and finish before the end of the period. Note that only condition C5, which is with respect to the schedulability analysis, was formally proven before, and the remaining ones are yet to be proven. In this talk, we address that gap in prior work and show how we can formally verify condition C1 to C4. In addition, we also propose a new safety condition that ensures progress. Even though this is not required for the correct behavior of the system, the previous conditions do not consider the case where the output of the hypertask would always be used, and if that would be the case, then no progress would ever be made. So condition C6 says that if the guest task finishes before the deadline, then the output of this task is used as the output of the mixed trust task. This condition, together with C4, that says that the guest output is the product of a computation in a single period, guarantees that if there is a valid run of a guest task, then that output is used instead of the hyper task. Let's define what is a valid run of a guest task. We denote as guest job the job run by the guest task, and by hyper job the job run by the hyper task. A valid guest job is one such that the job starts after the beginning of the current period and finish before the deadline of the guest task. Note that if more than one guest job was run in the same period, as a convention, we will consider as valid only the first one. In green, we highlight the valid guest job since it starts after the beginning of the period and finishes before the guest task deadline. An example of an invalid job would be one that would start after the period, but will end after the deadline. Another example of an invalid job would be, for instance, one that would start after the period, but will actually end in the next period. To have a valid execution of the mixed trust framework, we have the following properties. The hypertask only runs one hyperjob in the same period and always terminates before its deadline. We can enforce this since the hypertask is run in a protected and verified micro-hypervisor, and prior work has proven that it will have enough time to execute its job. The output of a valid execution will be either the output of the guest task, if there was a valid guest job, or the output of the hypertask otherwise. To prove these properties, we will need to model our synchronization protocol and then show that these properties are all on the model. In this work, we will be using UPAL to model the synchronization protocol. UPAL uses a modeling language that is an extension of time automata, which includes bounded discrete variables for addition state information, as well as broadcast synchronization channels. Time automata are often used to model real-time systems, since it provides finite state machines with clock variables, where all clock variables progress synchronously. Since we do not trust the guest task, we build a simple automata that represents all possible behaviors. For those unfamiliar with time automata, we have a starting node denoted here by this double circle, and each has as a pre and post condition. For instance, the edge below has the precondition that time has to be greater than 0, and then we'll actually trigger, we will use a broadcast channel start, and then we'll have the post condition that time will be reset to 0. The hypertask automata should be responsible for guaranteeing the correct output signal is broadcast for the mistrust task. If the guest job execution is valid, then the output signal should be broadcast. Otherwise, the HT output signal, which corresponds to the output signal from the hypertask, should be the one broadcast. So we'll have two cases. Let's consider case 1, where is the first case highlighted here in yellow, where in this case the start signal is never received. So that means that when time is greater or equal than the deadline of the guest task E here, then the hypertask will broadcast an HT output signal indicating that the output of the hypertask is the one that should be used. In case 2, the start signal is actually received, so the automata transitions from the initial state down to this other state, the wait state. And then it will wait there for an end signal. Now we have two subcases, case 2a, where the end signal is received before the clock reaches E, then we have a valid guest task execution, and the output signal is broadcast. And this happens here by doing this. The other case would be case 2b, where if the end signal is not received before the clock reaches E, then the automata goes from the wait state down towards here, and then this means that the HT output signal will be broadcast, which indicates that the hyper task output should be used instead, since we have an invalid guest task execution. So given this model, we want to prove the following properties that summarize the conditions presented previously. Namely, we want to prove that P1, each mixed stress task must produce an output every period. P2, there is only one output per period. P3, if the guest job execution is valid, the output is from the guest task. P4, if the guest job execution is invalid, then the output is from the hyper task. Since UPAL specification language is restricted, we have some limitations, since this language does not allow us to write temporal formulas with alternating temporal logic operators. Therefore, we need to construct two observer automata that will make our life easier to write the desired temporal logical formulas. Okay, this two observer automata, one of them is going to be with respect to the output. So it's built to track the behavior that relates to properties P1 and P2, namely that exactly one output will happen per period. Since we want to prove safety properties, this means that nothing bad will happen during the execution of all possible executions. Our temporal form will take the form of AG not F, which means that not F will hold in the current state and in all paths of executions, right? And this output of observer automata is basically just checking that, right? Just counting the number of outputs that were observed in a single period and checking who actually was responsible for the output, if either the guest task or the hyper task. To prove these properties, we write the following temporal formulas. The first one says that it's always true that we never observed that at the end of the period we had 0 outputs. And similarly, the second one says that it's never true that we'll have more than one output. To track the other properties P3 and P4, we built a job observer automaton, and this automaton tracks the start and end signals that are sent by the guest task to determine if the guest task job execution is valid. In particular, if the start and end signals are received in that order and within one period before the clock reaches E, then the job execution is valid, otherwise the job is invalid. So basically here in this job observer automaton, we can see that basically we are tracking if we receive a start and end signal before time reaches E, and if that's the case, then we will go to this valid state. Otherwise, we'll end up in this invalid state that denotes if the guest's job is valid or invalid. These properties can be proven with the following temporal logical formula. The first one denotes that it's never true that we can reach the valid state and the output being from the hyper task, which means that if the guest job is valid, then the output must be the one from the guest task. Similarly, the second formula says that it is never true that we can reach the invalid state and the job being from the guest task, which means that if the guest job is invalid, then the output must be the one from the hyper task. Okay, so we use UPAL to prove these properties for arbitrary values of the guest deadline and periods up to a given threshold. We can see that we were able to successfully prove these properties in less than 1 minute here. The time needed for verification grows with the increase of the possible values for the guest deadline and the size of the period. However, if we would like to prove the same properties for predefined values of E and T, then the verification would be very fast and will take less than 1 second. Even though the current time automata look simple, there were multiple modeling challenges that we need to overcome. For instance, to avoid zero executions, this means multiple events from occurring simultaneously or having infinite discrete events occurring in finite time, we had to be careful on the conditions and invariants that we assign to each edge. The model, although simple, was a product of the iteration of multiple refinements. These refinements were both done to improve readability and to make the model simpler, as well as to fix incorrect early attempts that did not satisfy the desired properties. Also, the model was very useful to allow us to detect a critical flaw in a previous implementation. And this was done because an early model that we tried that was faithful to the previous implementation did not satisfy the desired properties. When modifying the model, we noticed that the verification properties are tightly connected with detecting a start and end of a guest job. In the previous implementation and earlier models, we used a different methodology to detect the completion of a job. In particular, we would only track the end of the job. However, this has an issue of when a job ends, we do not know if it started in the current period or in the previous period. And this would break this property C4 that says that a guest output must be the product of a computation that executes within a single period. For instance, consider an invalid guest job where the end is in a valid time, but in the wrong period. With the previous implementation, since we're only tracking the end of the job, we would actually classify this as a valid job, even though it's not. In order to fix this issue, we modified both the model and the implementation to track both the start and end of a job, and therefore we're actually able to satisfy this property. So when dealing with complex systems, it may be infeasible to verify every component. In those cases, we can use a mixed trust framework that allows untrusted components to coexist with trusted components. However, even if we verify the trusted components, we must also verify the interaction between the untrusted and trusted components. In this talk, we show how we can model this interaction in McCall and increase our assurance in the correctness of the properties that we want to enforce. The model helps us to improve the implementation. However, there is no guarantee that the code satisfies the model. Even though we built the model as faithful as possible to the implementation, to guarantee that the model and the code are actually equivalent with respect to the properties that we're verifying, we plan to explore the following directions in the future. Either we can automatically generate C code that follows the UPAL model and then verify that the translation is correct, or we can actually verify the temporal properties directly at the code level and show that the code also satisfies those properties. By doing this, we will then be for sure have the guarantee that both the model and the code satisfy the same properties. Mixed trust frameworks are great and allow the interaction between untrusted and trusted components. In this talk, we showed how we can verify the synchronization protocol between these components and increase insurance in this framework. We encourage you to try out the mixed trust framework and its potential uses for your applications. Thank you for your time, and I'm looking forward to see you at the virtual conference where I'll be open to questions.